Oh, right, if there are people on Zoom, so they can hear you, then the mic
Hear
is.
you and test.
That reminds me that I should use this mic for the intro.
Is this audible? Should I move it?
Yeah, I mean,
Should I
people in here don't. Oh, I guess you could, because I'm not quite sure. Because I'm never on the other end of this.
Oh.
All right, yeah.
Yeah.
It should be. Okay, hello, everyone. Ooh, is that interference? Let's see. Well, thank you for joining today. I'm happy to give you one of Yale's newest faculty members, Earl Bellinger. He joined us in January. He has a long academic history, which I will summarize as having done undergraduate degrees in applied math and computer science, a master's at Indiana University in computer science, and then joint Ph.D. program, or somehow a joint Ph.D. in astronomy and computer science with joint university affiliations, both here at Yale and the Max Planck Institute in Göttingen?
Yeah, good to go. Yeah.
And then there was another university on there too. I forget which it was, or institution. Anyway, let me not try to summarize it all. Let me just let him take it away. He will tell us something about data and stars.
Yeah, very good. Thank you so much, Dan. Well, let me begin by saying thank you for inviting me to give this colloquium. It's great to be here. And I'm really happy to have the opportunity to speak in front of all of you. Most of all, because I hope to kind of start forming a bridge between our departments. I think that we have a lot to offer one another, namely you have skills and we have data. And so, that could be a really good partnership. And so, yeah, I noticed that half the room is astronomers, but I am going to try to pitch this for the computer scientists and not try to assume too much astronomy knowledge. Nevertheless, if I do use some jargon, please feel free to interrupt me and ask questions, and I'll try to take it slowly. Yeah, what else to say? So I wanted to begin our story with Eddington, and the main reason actually is because we had an eclipse on Monday, and it's just a beautiful piece of history of astronomy, which is that shortly after Einstein published his theory of general relativity, that came along with the prediction that the rays of light from stars would be bent around the immense gravitational field of the sun. And Eddington went on an expedition to measure this. And so this was like an early great test of general relativity. Now, that made Eddington something of a celebrity when he was able to measure the bending of the light rays by the sun. But what us in stellar physics know and remember him for are his great contributions to our understanding of the internal stellar structure and pulsating stars. Now, in his textbook in 1920, he has this famous quote where he kind of speculates that the interior layers of a star are some of the most impenetrable areas in the universe. What appliance could pierce through the outer layers and test the conditions within? Eddington already knew the answer at this time, although we sometimes like to play coy in talks and pretend like it was some mystery for him. But in fact, what Eddington was getting at is that stars pulsate. And the pulsations of these stars that tell us about their internal structure, and it turns stars into laboratories for testing physical theories. So in the 1960s, some researchers at Caltech pointed a spectrograph at the sun, and they said that they measured velocity fields in the solar atmosphere. This was quite remarkable. Most people don't know or appreciate that the sun is in fact a pulsating star. But it is, and the fact that it took to measure this can show you basically how subtle these pulsations are and how difficult it was to measure them. And so here you can see kind of a zoom in. By the way, I don't know if there's a camera or a place I should stand or anything. Am I free to roam about the cabin?
So that camera should be capturing you, I think.
All right, very good. Okay, I'll just assume I'm in the
But
field of
it's
view.
but I think it actually only captures things from like the middle over there.
Okay, so now
I'm sorry.
illustrations on this board for the computer science scientists. All right, so these pulsation modes that we can measure in the sun, they probe different depths in the star. Some of them are only shallow. These are modes of, we would say, high spherical degree. They tell us about the outer layers of the star. Really, truly global modes that sense the deep internal structure of the sun. And so measurements of these modes then enable us to determine the structure of the sun.
Can I ask
Yeah,
how
please.
they are measured? I mean,
So in
I know
this,
about size-
right, exactly.
we don't put them on the sun.
So in this particular case, it's a spectrometer. You have a basically an absorption line from, I think it's calcium, and you can see how the calcium line moves back and forth. And you get, I'll show you.
So it's a frequency shift.
Yeah, exactly. Yeah. And I'll show you how this is done in photometry later. So for other stars, you just take a photometric detector and you see how the light bounces up and down. And you have to disentangle that complicated signal into the spectrum of oscillation modes. Thank you for the question. I hope that clarifies it. And yeah, and in fact, that's why this is a velocity field. So it's like a Dopplergram, basically. You can see the velocities on the surface of the sun, and by disentangling that across the disk, you can then measure the frequencies of these pulsations and their amplitudes. Yes, so that then was instrumental in revealing the internal structure of the sun. So just like earthquakes tell us the structure of the earth, sunquakes tell us the structure of the sun. And it has confirmed that our model of the internal solar structure is essentially correct. So the sun has a nuclear burning core that's converting hydrogen. The energy from that is radiated out until the outermost 30% or so by radius, in which case the energy is then turbulently transported by convection. And it's in fact that turbulent convection that excites these oscillation modes in the first place and allows us to see them. Now, trivia question, does anyone know the typical period of solar oscillations? How long does it take for the sun to pulsate? Anyone know?
Guess half a second.
That's it. That's actually a good guess. So a lot of people get confused and they conflate it with the magnetic cycle, which is 11 years. But this is actually far faster. Typical period is 5 minutes. So the sun is pulsating in a huge number of oscillation modes, thousands of oscillation modes simultaneously, all around a characteristic period of about 5 minutes. And yeah,
Just to be fair, like, I didn't confuse it with the magnetic cycle. What is the magnetic cycle? I haven't.
okay. So the sun has spots on its surface, and these appear and disappear over a cycle of about 11 years.
Okay.
And so the sun becomes magnetically active, and then the surface gets filled with spots, and then it becomes magnetically inactive, and then you get kind of a clear
And
disk.
it affects radio communications here.
Yeah, that's right. So these measurements of the solar interior then enable us to test our theory of how stars evolve over time, so stellar evolution theory. So this is possibly the most famous diagram in astronomy, not necessarily this incantation of it, but simply plotting luminosity against temperature. This is the famous Hertzsprung-Russell diagram discovered over 100 years ago, and it's our basic way of diagnosing how stars live their lives. So on the y-axis, you see basically like the surface brightness of the object, and on the x-axis, you see how hot it is at the surface. And so for our sun, this is the zero-age main sequence. This is when it was born 4.5 billion years ago. And in the past 4.5 billion years, it's only moved up maybe about 20% in this luminosity, and it's gotten a bit hotter in that time. And so this is the solar symbol marking the spot of where the sun is in its present time. The sun is fusing hydrogen into helium in its core. That's dictating its evolution along the so-called main sequence, which is this first part. In a few billion years, the sun will exhaust its central hydrogen supply, and it will evolve into a subgiant star and eventually a red giant star, where fusion of hydrogen will continue in a shell surrounding the inert helium core. And finally, up here, after climbing the red giant branch, this inert helium core will ignite the helium will ignite. The sun will generate basically as much energy as a small galaxy all at once in a very short amount of time, and then it'll turn into a core helium burning star. And then eventually it'll evolve off into a white dwarf and cool off essentially forever until protons decay, something like 10 to the power of 100 years. So this is the evolution of the sun, and of course we want to test this picture. We want to understand if our theory of stellar evolution is correct. And so the sun provides a great benchmark for that. So let me give you a brief schematic of how this is done. So here I've plotted two evolutionary tracks of stars with masses near the mass of the sun, but not exactly the same. And again, this is the same diagram, the Hertzsprung-Russell diagram. And this Hertzsprung-Russell diagram is going to come back time and time again. This is, an astronomer's favorite plot, Hertzsprung-Russell diagram. So here are two stars that evolve in this diagram. You can see they live their life until a certain point. And over here, I'm plotting what their internal structure looks like as they evolve. Now, the thing to know about these oscillations we see in the sun is that they're sound waves, right? So the sun is basically a giant musical instrument ringing with all these frequencies. And well, what determines the frequencies of these oscillation modes? The internal structure of the sun determines it. What is the principal thing that matters here? Since they're sound waves, it's actually the speed of sound. That's actually just the ratio of pressure to density inside of the star, and those quantities evolve as the sun evolves. You can see, for example, as these stellar models evolve in their lifetime, so too does their internal structure evolve. In fact, you can see, for instance, the sound speed in the central regions lowering as hydrogen is converted to helium. You can also see the stars expanding as they evolve. So helioseismology, pulsations of the sun, present the opportunity to test this picture because by measuring these different oscillation mode frequencies, we can then infer the internal sound speed profile of our sun. And then we can contrast that measured sound speed profile with the profile given by theoretical models of stellar evolution. And so here you can see a classic exploration done by JCD in 1993, where he contrasted the sound speed profile of the actual sun and several different evolutionary models that he's constructed. So there's several things to note here. First of all, you notice we're looking inside the sun, so that's pretty cool. The y-axis is the difference between the sun and models, and you can see here that the scale is 1%, right? So our models of the internal structure of the sun, as given by stellar evolution theory, differ by no more than 1% with our measurements of the actual structure of the sun. That's remarkable. I mean, that's phenomenal accuracy by astrophysical standards. Normally, you're happy if you're within a factor 2 or something like that, factor 10 maybe. I mean, 1%, that's truly a triumph. Now, the other thing to notice here is that there's 4 different models. 3 of them include the effects of diffusion and 1 doesn't. So diffusion is these heavy elements settling into the sun over billions of years. And what you can see is that all of these models that incorporate the effects of this additional physical prescription into the computation of the models, they reduce the disparity between the actual sun and the models of the sun. And so this means that the sun is actually a laboratory that we can use to test physics of stellar interiors. The last thing you'll note is actually that none of the models are perfect. Even though the scale is small, these are highly significant differences. The error bars are too small to even be visible here. This is something like a 60 sigma difference between the models and the observations. And this is a problem that persists to this day. So we still do not have a perfect model of the sun, but it's darn good. I mean, it's probably the best model of anything we have in astrophysics. Okay, but this talk is not really about the sun itself, but about the opportunities we now have to do a similar thing for other stars. Now, I mentioned that we only discovered that the sun is pulsating in 1962, right? From which we could infer that the amplitudes of these pulsations are extremely small. That means it's also difficult to observe them in other stars. Fortunately, some space telescopes have begun observing and given us the data we need to find solar-like oscillators in our galaxy. This can only really be done for nearby stars. And the game kind of started around 2010 with the CROW mission and then really took off with the Kepler mission. And a lot of what I'll be talking about today is focused on results from the Kepler mission. Yeah, and another thing you can see here is that red giants, their amplitudes, so red giants are obviously more luminous than the sun is. And so they're easier to see at greater distances. And it also turns out that the amplitudes of their pulsations are greater. So we find far more pulsating red giants than we do dwarf stars. The sun's called a dwarf, by the way, in case you didn't know that. We have a humble star that we live around. Okay, so we're about here now chronologically. Currently, the TESS mission is ongoing, discovering these things. I should point out that we're really profiting by piggybacking off of the exoplanet hunters. So us seismologists, us astroseismologists, we have basically the same requirements that the exoplanet people need. To discover an exoplanet, you stare at a star for a long time and you wait to see the planet pass in front. And so the starlight dips from the planet passing in front. So you want to stare at a lot of stars and you want to take images as frequently as possible. So the Kepler mission looked at something like, I don't know the exact numbers, maybe 150,000 stars, and took an image approximately once per hour, sorry, once per minute. And with that, because obviously since the sun is pulsating with a period of about 5 minutes, you need to observe more frequently than that in order to resolve the oscillations. So Kepler did that for 4 straight years, once per minute, taking an observation, and that was sufficient to resolve these oscillations. Now, the future for astroseismology is very bright. We're about to enter the big data era with WFIRST and especially the Plato mission. So I'm one of the scientists working on the Plato mission. I'll say a little bit more about it soon, but you can see that we're going to get something like 10 to the power 7 solar-like oscillators. So astroseismology is entering the big data era, which is a great opportunity for those of you who like to work with very big data sets. And that's something where I think hopefully we can have some collaboration between our departments. So what did Kepler give us? So here's 1 week of photometry from Kepler. As I mentioned before, Kepler's basically a photometer. You look at the starlight and how it bounces up and down over time. And this is what you see. And it doesn't look like too much in this view, but when you take a power spectrum of this, then clear astroseismic signal emerges. So here I've plotted the frequencies and the power of those frequencies, and I've indicated the oscillation modes that are visible in this diagram. So unlike the sun, where we can see thousands of oscillation modes, due to the fact that we only get integrated starlight, we only get the global oscillation modes, and we get about, in the best targets, we get about 50 or 60 oscillation modes. I should point out the units. So microhertz are the preferred units of the astroseismologists. I mean, maybe some people prefer cycles per day in the back of the room, but no, I'm not sure. Maybe you're probably also a microhertz fan.
I also like this one.
Yeah, okay, very good, very good. So 3000 microhertz is about a period of 5 minutes. So that's a useful scale of reference. So what you can see is that there's basically a Gaussian power excess here. So this is described by a single number that we call nu max. That's the frequency of maximum oscillation power. You can also see that there's a characteristic spacing between these. So this is not a random pattern, but in fact, the oscillation mode frequencies are highly structured. So what am I talking about here with these different mode types? Well, for instance, this is what a quadrupolar oscillation looks like. Now, this is a highly exaggerated view. I told you that the amplitudes of these oscillations are small, so it'd be more or less like maybe the first frame of this image and no more. If you had some dramatic excitation process, you could actually probably deform a star like this, but that's not really what we're observing. I mean, these powers are very small. The other thing is that you can see there's a lot of structure to this data. So modes of the same degree, right? So for example, you have all these consecutive radial modes. They are separated by a characteristic frequency. So when I say radial mode, it's just kind of the whole star moving in and out. And there are modes of the same degree, but different frequency, because you can think of there being shells inside the star, right? So instead of just the entire star moving out, you can think of part of the star moving out while another part of the star contracts with the same frequency, and many shells on top of that. So this is probably we would call a radial order of, let's say, 20. So that's 20 shells inside the star, expanding, contracting with that pattern. So modes of the same degree are roughly evenly spaced, right? You can see the even spacing. And this is called the large frequency separation. This turns out to probe the mean density of the star, root mean density. So if you measure this, if you can measure this quantity in the star, you can measure how dense that star is. There's also this other quantity called the small frequency separation. You can see that they kind of follow this strict pattern where the L equals 0 and L equals 2 modes all go together. Now this is very interesting. It turns out that this quantity probes the mean molecular weight gradient in the core of the star. Now, if you remember, I showed you that a little bit earlier, what that looked like. As a star converts hydrogen into helium in its inner layers, that mean molecular weight gradient adjusts over time. That means that this is probing how much helium is in the tank. That means this tells you the age of the star. Aha, so astroseismology gives us stellar ages. And what I'll be telling you about is how this is an extremely interesting probe. I mean, normally, how would you know how old a star is? Now we can measure it. So in order to interpret these measurements, we need theoretical models. I showed you some theoretical stellar evolution models on some earlier slides. Well, how are they made? So I'm part of a collaboration called MESA, Modules for Experiments in Stellar Astrophysics. This is an open source software project where we provide the calculations to compute how a star evolves over time. You can put in different masses, different initial chemical compositions, different physics, like for example, you can turn on or off diffusion, and you can include different treatments for how convection operates, and this software will compute for you how those stars will evolve. So you can download it, run it on your laptop. And this is probably one of the most visible open source projects in all of astronomy. We now have 6 instrument papers. And yeah, this graph is basically showing that these papers have been cited a good amount of times. And then the papers that cite those papers have also been cited a good amount of times. So a big impact multiplier. And we do a lot of things like we put on annual summer schools. We do continuous integration testing of all of the Git commits. We try to involve the community in our development. And yeah, we're just an ongoing active project. And so this is how we carry out these stellar evolution calculations. Okay, and then we want to interpret these observations. And so here's where we get into some more of your domain. So here I put up a very schematic view. And actually, I think it's probably most interesting if I don't get into too many of the details and instead leave that for you folks to come and talk to us about, good ways to get involved. But a basic schematic could be that on the left, you input your data. It gets processed by some large number of, let's say, hidden neurons, for example, that have been trained on theoretical stellar evolution models, and out comes your distributions of, for instance, the age of the star, its mass, its chemical composition, and so on. We've done a lot of different variants on this theme. I'll show you just one. So Mark's in the audience. A few years ago, when Mark was a Ph.D. student, he led this paper where we used the convolutional input. So it's not exactly this. This is more of a schematic view, but you put in basically an image of your observations. It gets processed through a neural network that's been trained on a huge corpus of theoretical stellar evolution models spanning basically all the uncertainties and all the degrees of freedom in your models. And then on the output side, you have a mixture model that then gives you distributions of your quantities of interest. Of course, another good way of tackling this problem is sort of in reverse, where you take all this stuff and put it on that side and vice versa, and build an emulator and then use sampling methods. It's a good way to tackle this in a principled way. Okay, so what do we get? What do we get from astroseismology? We took 100 of the best observed stars from the Kepler mission, and we put it through this machinery to infer the parameters of those stars. It turns out that from seismic data, by interpreting them using theoretical stellar evolution models, you can measure the surface gravities of stars to about 0.1%. You can measure the radii, or the sizes of the stars, to about 1%, their masses to 3%, and their ages to 10%. Okay, maybe that doesn't mean anything to you. So now I'm going to start to tell you what we can do with this level of precision, because astroseismology essentially provides us with some of the highest precision measurements in all of astrophysics and enables some exploration that wouldn't otherwise be possible. So my plan for the rest of the talk, and I guess I have like maybe until what, 12:45 or so? Oh,
One is fine.
one? Okay. I'm going to very briefly go through each of these 6 topics and share 1 or 2 slides on each of them and say how astroseismology is shining a light on each of these different areas. So
Could we go back? You mentioned training data to the network there.
yeah, sure.
One ahead now. You mentioned training data there. What's the training data here?
Okay, yeah, great question. So in this case, I generated a very large dimensional grid of theoretical stellar evolution models where I spanned basically all the different inputs you can give to a theoretical stellar evolution model. So that's the mass of the model, the initial helium abundance, the initial metallicity, so how elements heavier than helium, the efficiency of convection, which sets the size of the star, the strength of diffusion. So instead of turning it on or off, I allow various diffusion coefficients. The treatment of convection. So you saw earlier that the sun has this convective envelope. Stellar evolution theory can't actually predict how deep that envelope should be. Basically, it should be some amount deeper than that. That's more or less like a minimum deepness, but we don't know how deep it should actually be. So we have 3 parameters associated with extending the size of that convection zone. Of course, the age of the star is another independent variable. For them all. That might be the various degrees of freedom. And so what I did was I used Sobel numbers to quasi-randomly generate a large list of initial conditions and computed as many models as was feasible. And then gave these models to Mark, and Mark trained this network to be able to do this inference problem. Yeah, I should mention Mark is visiting just for a couple days, so he's around in case people want to chat with him. Mark carried out this work as a PhD student, but then went on to become Hawaii, and now he's a postdoc at MIT. All right, did that address your question?
Thanks.
Okay, very good. Thank you for. Okay, so we have these precise measurements. Let's put them to use. All right, exoplanets, other worlds. Well, I mentioned that if you want to study an exoplanet, one way of doing it is waiting for it to pass in front of the star and seeing the starlight dip. Okay, but what do you get from that? Well, it turns out if you can measure the dip and you know the radius of the host star, then you can get the radius of the exoplanet. Well, how do you get the radius of the host star? Astroseismology is the best game in town. And so here you can see that to first order, with which you measure the size of your exoplanet depends principally on the uncertainty with which you can measure the radius of the host star. And so it's pretty good agreement in these uncertainties. Here's the band of measurements that are enabled by astroseismology. So the best characterized exoplanets are the ones for which their host stars have benefited from an astroseismic analysis. Once we've derived these exoplanet characteristics, we can then play a similar game by constructing theoretical planet evolutionary models, and then build again a mixture density neural network that allows us to infer, for instance, the relative thicknesses of the layers in that exoplanet. So this particular exoplanet has like a fairly large core. It may or may not have a mantle and some ice layers and a gaseous layer as well. That's more or less everything I want to say on exoplanets, so I'll just move on. Okay, so the next topic is galactic archaeology. So we live within the Milky Way galaxy, which has some 200 billion stars. And we would like to understand how our galaxy formed and evolved over time. What are the ingredients you need in order to do that? Well, you need to know the motions of the stars. So we get that from kinematic data from the Gaia spacecraft. You need to know the chemistry of the stars. So we get that from large-scale spectroscopic surveys that tell us, for instance, their metal abundances. And of course, you need to know the ages of the stars, which is provided by astroseismology to 10%. Kepler looked at one fixed field of view in the sky for 4 straight years and took an image, or took a measurement once per minute. It was only this tiny postage stamp in the sky. The Plato mission is now going to do this at an industrial scale, basically looking not at the entire sky, but most of the sky. And it's going to be downlinking 200 gigabytes every single day. So we do have a big data problem, big data opportunity to address with astroseismology. So this is going to really allow us to understand the formation and evolution of our galaxy. An exciting opportunity that this enables is to be able to contrast the measurements of our galaxy with simulations of our galaxy. So these are cosmological zoom-in simulations. Here, these researchers simulate the entire universe, no small task, and then they zoom in on a small box and they find galaxies similar to, for example, our own Milky Way. And then with these theoretical galaxies, you can then look at the stars that are observable if we were an observer in that galaxy, and we can contrast that with the picture that we have from the measurements we get with things like Kepler, Gaia, and the forthcoming Plato mission. And this will allow us to test our understanding of galaxy formation theory in a new way. It's also important for us to be able to deal with low signal to noise data, because this can extend the reach of astroseismology. So our guest this week, Tim Betting, has probably, I think, the most highly cited paper in astroseismology. I checked this morning at 981 citations, so that's darn good in astronomy. In that paper, he showed how you can take these simple measurements. I pointed out earlier the frequency of maximum oscillation power and the average spacing between radial mode frequencies. You can combine that information to get inferences on the star. So in this paper, I looked at how we can make use of basically low signal to noise data and found basically various patterns of how we can make these measurements, even if we can't resolve the individual oscillation modes in these stars. And found, for instance, that the scaling with the radius that still gives us radii of stars, no longer to 1%, but 6% is still really good, and will allow us to measure stars all throughout our galaxy. A further opportunity is to go beyond our own galaxy and go to other galaxies. So I mentioned in the beginning that we can only measure these small amplitude pulsations in nearby stars, right? Sun has small amplitude pulsations. Sun-like stars have small amplitude pulsations. But once you get to giant stars, their amplitudes are much larger. And in fact, there's a specific type of giant star called a Cepheid that we can view in other galaxies. Now, normally, you can't infer too much about the properties of these Cepheids. But in this paper, we again used machine learning methods. But here, instead of on the frequencies themselves, in Cepheids, you only get one period of pulsation typically. And so there's no spectrum of pulsations to benefit from. You just have one period. But in fact, you have this interesting shape to the light curve. So this is how the star is appearing to get brighter and dimmer over time. So we used time-dependent pulsation models in order to model these variations in the light curve shape itself. And from that, we found out that we could actually derive parameters such as the mass of the star based on that light curve shape. I think for the first time. And so we were able to apply this to over 10,000 pulsators in other galaxies, which in turn has allowed us to determine things like the 3D geometry of some of those galaxies. This field's going to be blown open in the next few years. Not only There's also the ground-based LSST. The Milky Way is surrounded by something like 100 dwarf galaxies, and there's several astronomers in here who are working very hard on studying those dwarf galaxies. Those dwarf galaxies are home to some of these large amplitude pulsating stars. We're going to be able to start putting together a picture of how those dwarf galaxies, their shape and morphology, perhaps even how they formed and evolved. I wanted to throw in just a quick slide on explainable AI. I probably don't have too much time to get into the thorny details of it, but basically, we want to try to use methods to also understand our own data a bit better. And so this was just an exploration that I carried out with Salim Khalisi, who's going to be joining our astronomy department as a PhD student later this year. So he did an internship with me last summer. We basically looked at feature importances in our input data, because we knew the period in this previous case, we knew that the period wasn't the main thing that was giving us information about, let's say, the mass of this star, because we only had that one period, and we knew it was the shape of the light curve that was doing the work. So what was it about the shape of the light curve that was doing the work? Well, we can come up with a simple mathematical description of that light curve shape as just a sum of sines, sum of amplitude components. And we saw that it was, in fact, the second amplitude component that gave us all that inference ability. In this particular example, it gave us the inference about the temperature of the star. And so what we actually found is that it doesn't vary in a monotonic way, but as a star changes in its temperature, this overtone in the light curve goes up and down. And so that's something you can actually see in the data. And this is kind of a nice data mining exercise that points us to some underlying physics of what's actually going on, what's actually enabling us to do these inferences, and gives us kind of some confidence that, that these methods are working, because you can look back at the models and say, oh yeah, what's going on? I can see this correlation here. Because of course, we want to avoid the situation like the classic computer vision problem, where you ask, why can the machine identify the husky in the image and it's the snow in the background and not anything to do with the dog itself? So here it is actually intrinsically related to some feature describing the light curve, and then we can look at the models to see how it goes. Okay, stellar physics. Okay, naturally this is the most profitable area of astroseismology, so I just crammed it in the middle. The sun has a nuclear burning core and transports energy away from that core using radiation. But if you pump up the mass of the sun, then its core will become convective. And instead of having a convective envelope, it'll have a radiative envelope. So the nature kind of swaps. But as I mentioned earlier, stellar evolution theory can't actually predict the sizes of these convection zones. It requires some additional physics that we're not able to simulate in these one-dimensional simulations. And while astroseismology allows us to look inside of the star and measure the sizes of these zones. And so I like this as kind of a nice illustrative example. Here we can actually measure the mass at which the cores of stars cease to be radiative and start transporting energy by convection. So we're really looking inside of stars. And thanks to these measurements, we'll be able to ideally, at one point in the future, develop a better theory that allows us to actually predict this in the first place. So these are constraining measurements. Inside the center of stars, of course, nuclear reactions are going off, but the rates of these nuclear reactions are, in many cases, actually quite highly uncertain. So the sun is generating energy primarily through the proton-proton chain, in which essentially you put in some hydrogen atoms, you get out helium atom, and you get out some great amount of energy through E equals mc squared. Well, in this paper, we looked at how constraining the structure of the sun itself is on those nuclear reaction rates. How much are you able to change the rates of nuclear reactions and still get a solar model that agrees with the seismic measurements of the sun? It turns out that in some cases, changing the nuclear reaction rate by more than 1 sigma of the measured value changes the structure of the sun by an intolerable amount. that implies that in principle, the sun can be used as a nuclear physics laboratory to measure these rates of nuclear reactions. Now, as I said from the outset, we don't yet have a perfect model of the sun. The data of the sun is better than the theory. And so I would say it's too risky at this moment to use it as a measuring device because there's other uncertainties that are greater than these uncertainties in nuclear reaction rates. Once we sort out those other issues and we have a sufficiently good model of the sun, then we'll actually be able to measure these nuclear reaction rates using helioseismic data, and I think soon, eventually, also astroseismic data. And in fact, it seems like in the fundamental reaction rate in the sun, turning protons into deuterium, basically, we might make it a 7-fold improvement in the uncertainty of this nuclear reaction rate. So might even have practical value, maybe. Not usually the goal in astronomy, but maybe. Okay, since our measurements of these stars have revealed that our models are good but not perfect, that then presents the opportunity to ask, okay, what's wrong with the models? Okay, where can the models be improved? So this brings us to the structure inversion problem. And so Philip Frank is also visiting us this week. Philip's an expert on these inverse problems. So I'm going to tell you a bit about the classic way that we've been doing it, borrowing from helioseismology. But very recently, Philip and I have been working on more modern ways using information field theory, of which Philip is an expert. So the basic problem is you have this model of the star, and it doesn't pulsate exactly as the star pulsates. That implies that the internal structure of the model is not exactly the same as the internal structure of the star. And furthermore, the space of models given by stellar evolution theory does not include the actual star, right? So you have to leave that space. When we go to the more general space of all possible stellar structures, not the more limited space of the space of structures generated by our current theory or current understanding of stellar evolution. So given that they pulsate differently, we have this difference in pulsation frequencies, we want to infer the difference in the internal sound speed profile between the star and the model. And that can tell us where exactly in our model the physics is wrong, right? So these are mediated by so-called kernel functions that tell us the sensitivity of a given oscillation mode to the internal structure of the star. And so this is an ill-posed inverse problem, and we want to infer these differences. So first, we applied it to probably the most sun-like star we know, happens to be called 16 Sig B. And we found very broad agreement between the internal structure of that star and the internal structure of our best fitting stellar evolution model, with uncertainties to the scale of about 5%. Remember, we get 1%, much less than 1% in the sun, and that's because, the sun's right there. These stars are far away. So in this case, for a very sun-like star, the models are actually very good. My PhD student in Germany, Lynn Buckley, is actually visiting Yale currently, so you have time to talk with them if you like. Lynn's been applying these techniques to many more stars that have been observed and has found much more significant differences between the internal structures of stars and those of the models. In this case, a greater than 3 sigma difference in the internal sound speed profile deep in the core of the star. This is like maybe 5 to 10% away from the center point of the star. We can see very clearly that our best fitting theoretical stellar evolution models are insufficient at describing the star, which also means that when we apply, for instance, these machine learning methods to characterize the ages of these stars, these systematic errors creep in there and are not accounted for. So we have systematics owing to the fact that our evolutionary models are not perfect. So what effects could make a star differ from normal stellar evolution theory? Well, one possibility is that, our understanding of stellar evolution isn't that great, and that may be true, but of course we saw in the case of the sun that it does an extremely good job. So I'll talk briefly about one effect that could change that situation, and that's the presence of binarity. So first things first, many stars are born in binaries, and we assume these stars to be born at the same time. Astroseismology, I think, gives really compelling evidence that that picture is actually right. So here I've taken, I mentioned 16 Sig B, here I've taken its companion star 16 Sig A. We've analyzed the seismic data of those fit stellar evolution models, and we see the posterior probability distribution. These stars have the same age. They were formed at the same time 7 billion years ago. So that's great confirmation of binary formation theory. It turns out that most massive stars are born in binaries. The binary fraction of stars greater than 10 times more massive than the sun is something like 100%. They're all born in binaries. And what's interesting is about a third of those will merge over their lifetime. So here's HR diagrams of normal single stars, and here's of binary merger products. There's a big problem in massive star evolution, which is that there's an overdensity of stars in this region. Now, I've colored this diagram by the longevity. These are the long-lived main sequence stars, and these are somewhat long-lived red giant stars. There should be a dearth of stars here. This is the famous Hertzsprung gap. But if,
I can't say what your pointer is. Could you use your finger?
Yeah, sure.
The density you just said.
So this is the main sequence where you have long-lived stars. These are red giants, which are also relatively long-lived. But these light points in the middle, this is the Hertzsprung gap, where stars cross this very quickly. And because they cross it very quickly, you don't expect to observe very many stars in here. In fact, this basically gives the ratio of how many stars you expect to observe here versus here. You should get something like 1,000 times more stars here than here. But in fact, the number's more like 30 times more when you look at observations. This is strongly suggestive that these stars might in fact be long-lived merger products that can live there for perhaps millions of years. And I won't go into the details, but in this paper, we say this is very suggestive because the models have them living a long time here. And then furthermore, if we can do seismology of these objects, we would be able to tell for sure. In the interest of time, I'll skip some of this. Yeah, I mean, this is just saying we can use machine learning classifiers to determine the stability of multiple star systems using n-body codes. Pavan just finished his PhD this week, so that's pretty cool. An extreme example of a binary star system is if you pass a star by a supermassive black hole. The enormous gravity surrounding that supermassive black hole can rip out the outer layers of the star. The remnant of that tidal disruption event can carry on its merry way and might look similar to a normal star. So this is showing just, tragic 10, 24 hours or so in a star's life where here it's a normal star, but then it passes by a supermassive black hole, it gets ripped apart and loses about half of its mass in about a day's time. And at first glance, you might not be able to distinguish these stars, but in this paper that we're still writing up, we show astroseismic signatures of how we can find the stars that have survived tidal disruption events. Yeah, I'll skip it. Okay, I only have some minutes left. Okay, I'll be very quick. Now we get to some fun stuff. In Einstein's theory of general relativity, the gravitational constant is the same everywhere and at all times throughout the history of the universe. But in theories of modified gravity, such as string theory, the gravitational constant gets promoted to a dynamical quantity that can vary throughout space and time. Well, the internal structures of stars would have something to say about that, because if they evolved in stronger or weaker gravity in the past, that constricts the realm of possible stellar structures that could exist today, and that would be reflected in their starlight through their pulsations. It can be shown that the luminosity of a star goes with the gravitational constant to the power 7. So if you cranked up the gravitational constant, then you'd make, for instance, the core of your star convective when it wouldn't otherwise be. And that signature would persist to the present day in some shape or form. So here we created a grid of models where we varied the strength at which the gravitational constant could have possibly varied over time, such that it arrives at its present day value today. And then we modeled an ancient main sequence star using this grid of models in order to constrain the possible variations in the gravitational constant over the history of the universe. We found that the gravitational constant could not have varied by more than something like part per trillion per year over the past 10 billion years in order to support this seismic data. And so in other words, so far, there is no astroseismic support for string theory, and general relativity is still the champion of gravity. Okay, and finally, this brings me to the last story I'd like to tell you today, which is about the vexing problem of dark matter. When we look out into our Milky Way galaxy, we see the mass budget. There's only about 4% of the mass in stars, 12% is in the gas that eventually makes up stars, and the remaining 84% is dark matter. This is supported by many different lines of evidence, such as the rotation curves of galaxies. Even our theory of galaxy formation itself requires this abundance of dark matter, where basically the gas falls in, and that's where the stars get made. But what is this dark matter? Well, about 0.1% of the dark matter is made up of about the 100 million black holes that have been created as the endpoints of massive star evolution. Stars significantly more massive than our sun will end their life in a supernova and leave behind either a neutron star or a black hole. And if you count up how many stars there have been in our galaxy, you take into account the star formation history, the lifetimes of these stars, you find that our galaxy is a graveyard of these compact objects, about 100 million black holes in our galaxy alone. But that only accounts for 0.1% of this dark matter. You also know that there's a supermassive black hole at the center of our galaxy, weighing in at something like 4 million solar masses or so. That accounts for 1/10,000th of the dark matter budget. There's also neutrinos streaming out of the sun and other stars. That accounts for some vanishingly tiny fraction of the dark matter. The remaining 99.9% of the dark matter is of unknown origin, and many people consider this to be the greatest unsolved problem in astrophysics today. So what is it? Well, nobody knows, but one theory goes back to Stephen Hawking, who speculated that it could be additional black holes that make up the rest of the dark matter. After all, we know black holes are basically one of the few things that we know qualify as dark matter. In this scenario, these black holes would have been made in the first second after the Big Bang. They would be so-called primordial black holes, and they would span all possible ranges of mass. They could be as light as an asteroid. They could be as massive as a supermassive black hole. And in fact, primordial black hole formation scenarios give a wide mass function, creating all of these just with many different proportions. That this line of reasoning, these primordial black holes, we don't know if they exist, but this line of reasoning was already scientifically fruitful. It was this thinking that led Hawking to his arguably greatest discovery, which is that black holes leak particles and evaporate over time. So Hawking radiation came from the consequence of contemplating primordial black holes. Hawking furthermore speculated that such a primordial black hole could accumulate at the center of the star like the sun, and he even said that it could be responsible for the, at that time, unresolved solar neutrino problem, which we now know has there being a black hole at the center of the sun. But this is quite interesting. If we imagine that we're in a universe in which these primordial black holes supply the dark matter, then our galaxy is totally full of these things. We are inundated in them. There would be about 10 to the power 30 primordial black holes of asteroid mass whipping around our galaxy. That is far more numerous than the 200 billion stars that make up our galaxy. They would have an average separation the same as the separation between the Earth and the sun, meaning that at any given moment, our solar system has a black hole. Now, if such a black hole, these primordial black holes are traveling around very quickly, maybe 200 kilometers per second. If such an object encountered the sun, it would just pass through it like a bullet. It might excite some oscillations temporarily, but they would just peter out and the sun would not capture it.
And if it hits us.
It would be bad. Yeah, they are very small. Even ones that are The smallest ones would pass through the Earth freely, but anything larger than that, you would actually have large scale destruction. And there's some nice simulations.
Would we know?
Yeah, sure.
Of
Yeah.
this force?
There was an event 100 years ago that was a candidate PBH transit that has since been ruled out, but this would be one of the low energy sites. Fortunately, you can do the calculation. Expect the Earth to encounter one of these something like once per its entire history. So, 0 or 1 times likely events. So we're not at great risk, even if it's supplying the dark matter. Whatever the dark matter solution is, the Earth's receiving a flux of it. We're going to get hit by something. So it might be these. Anyway, fully formed stars will not be capturing these primordial black holes. But due to the time-varying gravitational potential during star formation, a star one of these light black holes and then have it at its center. You might think that a star would just fall into a black hole, but these are extremely small black holes. The Schwarzschild radius is like smaller than the radius of an atom. And so it's just this tiny funnel where it's hard to pack particles into it. And so it's hard for it to double its mass at very low mass, even over the lifetime of the solar system. Yeah.
Sorry, why is the velocity argument different during formation?
Yeah, great question. So the basic idea is that if you have a fully formed star, and even if you imagine this black hole is at rest, it'll be accelerated by the gravitational field. It'll fall into the sun. It won't interact with any particles, so it doesn't get slowed down, and it'll just climb out of the gravity well without any interactions. But during the gravitational contraction, as it's falling in, it doesn't feel the contraction from the outer layers, and so the escape velocity is changing, and that provides a mechanism to potentially capture some small fraction of these black holes. It would be a tiny fraction. The vast majority of them would still pass through. Estimates give that something like, if we are in the scenario, something like 10,000 stars in the Milky Way would have a primordial black hole at its core. So you might think that the star would fall right in, but one thing you need to recognize is, in fact, black holes are the most efficient known engines in the universe. And so there is also the opportunity for them to radiate very efficiently. I mean, the particles that fall right in won't do anything, but typically they'll encircle the black hole and create an enormous layer of heat and friction. And that thing is luminous enough even to drive convection in the core of a low mass star like the sun. So I see I'm right at the end. So here's some luminosity curves of what the scenario would look like. So I modified MESA in order to account for a black hole eating a star from the inside in order to study its evolution and its seismic properties. So here's our normal sun. In the past, it was dimmer. It got to its current luminosity. In the future, it'll be brighter, and eventually it'll turn into a red giant and consume the Earth, probably. Sorry if that's news for you computer scientists, but I guess we're doomed from the red giant sun. The situation's quite different if you put a black hole inside the sun. So it grows to its current age. The black hole is growing on the inside. So here I've marked the mass of the black hole. Eventually, the luminosity outflowing from the black hole is so large that nuclear fusion in the sun would shut off. And this star would then become powered by the accretion of the solar plasma onto the black hole. And the star would puff up into a giant star supported by the accretion onto a black hole. Here's now a scenario in which that is clearly incompatible with our present sun because it would have already puffed into a giant star. So we can see that we can put a limit on how massive a black hole could be inside of our present sun, just based off of this alone. It has to be, less than, let's say, a billionth of the mass of the sun. One interesting thing to point out here is you see the simulation stop here before we get eaten by the red giant sun. So in a sense, this black hole would save us from the red giant sun. Nevertheless, it gets hot and luminous enough to boil off Earth's oceans. So in a sense, you could say the black hole sun will come and wash away the rain. All right, last thing I want to say is how these things evolve in the HR diagram. I told you this is our most important diagram in astronomy. This is the normal evolutionary track of the sun turning into a red giant star. here's what happens to these stars that capture a primordial black hole. You see that they dim over a period of perhaps 50 megayears and then brighten. And they live to the red of the red giant branch. This is an extremely sparsely populated area of the Hertzsprung-Russell diagram. Normal stellar evolution pathways don't make stars live here, and certainly not for long periods of time. And so it could be possible to find these so-called, I've named these Hawking stars in honor of the guy who suggested them. It could be possible to find these stars based on their position in the HR diagram. And because the energy flowing out from the black hole would cause the star to become fully convective, unlike normal red giants, which pulsate in mixed mode oscillations, these would have pure pressure mode oscillations. So if you find a red straggler pulsating in pure P modes, that's a key indicator that this star may have a black hole at its center. So I published this a few months ago, and it got highlighted by Science and Nature Astronomy, and of course picked up by YouTube. And so that's been kind of interesting to see, especially that I named this thing Hawking Stars, and I see Matt O'Dowd talking about it. So that's been kind of fun. In summary, astroseismology allows us to probe far-ranging physics, both by providing precise ages, masses, and radii, and through allowing us to test stellar evolution theory, including when we put fun physics into our simulations. And I'd like to reiterate what I said at the beginning. I hope some of you will be interested in these kinds of problems and you'll want to collaborate on them. We need your help. We want your help. We want you to come down and talk with us and help us push these fields forward. Thank you.
Let me just make a suggestion. I find Earl in the elevator or walking somewhere up to this building. Good strategy. We also probably still have some more food and coffee if anyone wants it. I don't know if you have time to stick around and talk to people, but if you do, we move back to the kitchen and common room. That's a great place.
Thank you.